Hello everyone, in this video I will introduce you with a new Morph finishing toolpath in SprutCAM 9. Morph is a toolpath that generates passes between two curves. Let's say we want to machine this surface. So we just create a new finishing Morph operation and add this surface to the job assignment as machining surface and add the top edge as the first curve and the bottom edge as the second curve. Now we go to strategy and say that the generated toolpath will be a 3D toolpath with fixed axis direction. Now we see the tool is not optimal, so we change it to a 4mm ball mill, and now we click run and see the generated toolpath. It is a long toolpath. That means that the passes that are generated move smoothly between first and the second curve. There are two more strategies available more. It is a cross toolpath, by which the generated passes are perpendicular to the first and the second curve, and the spiral toolpath. Spiral toolpath is not useful here, but because the curves are not closed, it is more useful for closed contours. Let's say we want to machine these surfaces. We just add it to the job assignment and specify the first curve and the second curve. And the strategy is spiral. So you can see that the resulting toolpath is a smooth spiral curve between first and the second curve. Okay, that's it for the strategy. You can change between 3 available strategies, across, along and spiral, and you can change the step. Let's say it will be 20% of the tool diameter. Okay. The cool thing about Morph is that Morph can be 3, 4 and 5 axes, and this is very cool. For example, we can machine this surface by normal to the surface simply by changing the tool axis orientation mode to normal to drive curves 5D and recalculating the toolpath. Now let's see what we get. Okay, we get a toolpath that is normal to the first and the second curve, but it's not optimal here. What is more optimal is to incline the tool in the direction to the first curve, and for doing it we introduced the lean angle parameter. This parameter specifies the angle at that tool will be inclined to the direction of the first curve. Let's say it will be 50 degrees, and recalculate. Now you see that the tool is inclined in the direction to the first curve, or we can change it to -5 degrees, and the tool will be inclined in the direction to the second curve. And this is a very useful parameter. Okay. Now I will show you some examples of Morph. this is a nice example, because on that example I will show you the concept of synclines. Let's say we want to machine this fillet. So we have added it to the job assignment as machining surfaces and specified the first and the second curve, and we did not specify any synclines yet. And the strategy is a cross. Let's calculate the two path, and we see that the two path is not optimal. It is so because the curves are not synced properly. And what does it mean? It means that when we move between the first and the second curve, we just connect points on this curve. And how we do it? If no synclines are specified and the curves are closed, we just take the first point on the first curve and search the closest point on the second curve and take those points as start, and then we just go along the first and the second curves and step across them and connect the points, and so we get those nasty passes. So how to tell SprutCAM what we want? It's easy. We just have to specify synclines. Let's say we just add one syncline here and recalculate the two path. Now we see that the first pass begins on this syncline and it is parallel to it, and then the two path moves steps along the first and the second curve and connects the points, and it's not optimal. So we just add more synclines and see what we will get. Let's add here and recalculate. Now you see that in this area the two path is good, and then it's not good. So we add syncline here and here and here and recalculate. Okay, now we have a nice two path. And we can change the strategy to spiral and change step to 20%, and we get a nice smooth spiral between first and the second curve that machines this fillet. Let's go to simulation and see what we have. Or we can machine this cool surface between the sharp edge and this edge. We just specified the machining surfaces and the first curve and the second curve, and specify some synclines, one here, and the other synclines I drafted into the geometry. You can see them here, here, and here. And calculate. Okay, let's change the mu mode to climb or to conventional. And alter the lean angle to 30 degrees. Likewise, we can machine the blade itself. We just create a new finishing morph operation and add the blade surfaces as machining surfaces. Then add first curve, second curve, and Synclines. Synclines we can just box pick and press the Synclines. Only the curves will be selected and added. Now the strategy alone, let's say it will be spiral and step will be 20%, and the 2-axis orientation will be normal to drive curves 4D. Okay, here I will introduce you with this 2-axis orientation mode. In this mode, the tool is oriented normal to the drive curves, which is this curve and this curve, but one coordinate of the 2-axis is zeroed. And what coordinate? It depends on the rotary axis parameter. In this case, we want that the z coordinate will be zeroed and global CSZ. Now calculate the two path. Okay, and go to simulation. Okay. Now we see that the tool is perpendicular to the z-axis of the global coordinate system. If we change the 2-axis orientation to normal to drive curves 5D, then the 2-axis will be not perpendicular to the z-axis of the global coordinate system. Okay. Now you see that the tool is not perpendicular to the z-axis, and that is not desirable in some cases. For example, if you have a 4-axis milling machine, okay. Now I will show you yet another example. In this example, we want to machine this blade. And we want the tool was directed to the normal to the surfaces of machining. And for that we have the 2-axis orientation mode, normal to surfaces 5D. The default is normal to drive curves 5D, and the toolpath in this mode is the following. Okay, I think in this area it's not so good, I think. We can make a better toolpath if we will position the tool normal to surfaces themselves. Instead of positioning the tool normal to the drive curves. Okay. Now I want you to demonstrate yet one example of Morph. Okay. Let's say we want to machine these surfaces. And we want to machine them such a way between this and this curve. the curves are not surface contact curves. These curves we drafted in 2D geometry, so we say that the tool have to be placed outside those curves. And let's see what we have. Okay, looks nice, and we can change it to a long. Okay, now you see the cool thing about Morph. This is actually the reason why we specify machining surfaces, because Morph generates two paths in such a way that it tries to machine only the machining surfaces. And so you can see here that the two path is not between this curve and this curve, but two path machines only the surfaces we added to the job assignment, and doesn't machine these and these. When we calculate Morph tool path, we search the two contact points with machine surfaces and generate passes only in these points. That's why we have these nice two path that touches only machining surfaces and not machines the surfaces we did not specify as machining surfaces. For example, we can say that this surface is also machining surfaces and recalculate the two path. Now you see that it's a different two path. Okay. Next section of this video is about linking options in Morph. In Morph, we introduced new linking options and new linking parameters. Let's say we machine these surface between these curves, and you see here these nice high-speed links. How we get them? We just set short link type to high speed, and high speed link means that when we connect the first and the second point of the link, we try to not exceed the specified smooth link radius. It's set to 1 millimeter here, but we can change it, say, to 2 millimeters, and now the links are bigger. And this is only one option we added. Yet another option is smooth link. Smooth link is a spline link. We just take a point and a tangent of the first connection point and the point and the tangent of the second connection point, and connect these points by a spline. And here yet another interesting thing you can see here. These vertical arcs, they have been added to the two path because of the smooth link radius parameter which is set to 2 millimeters. Let's zero it and recalculate. Now we don't have these arcs. So the smooth link radius parameter affects not only the high-speed links, it affects also the transitions between the vertical plunged and red tracks and the engaged. Let's show you some interesting things. Let's say we want to machine only in one direction, conventional, and let's say that the long link type, is it it's high-speed link, the short link type. Now you see this nice spiral. Isn't cool? Now let's say we want to machine along the curves and in one direction. And you see these spiral. It is a long link. We can change it to straight, or we can change it to smooth, or we can change it to high speed. Or we can change it to feed distance. Okay. The link by feed distance means that the tool moves at the feed distance to the air and then moves to the second point. For example, let's say that feed distance is 5 millimeters, and you will see the difference. And we have a link by rapid distance. It means that the two moves will be moved by 1 millimeter at feed distance and then by 5 millimeter at rapid distance. And you see here these vertical arcs that are introduced by smooth link radius. We can eliminate them by zeroing this parameter. And we have engaged and retracts as usual by tangent, by arc, by normal, and by line. That's it for now. Thank you for your attention.